AtomDB has been a long ongoing project for many, many years. This year's main updates are presented by me on behalf of the team. The major contributions this year from Randall Smith and our undergraduate student, Kerry Hewer, who has done fantastic work and is starting at Drexel in a few months, so look out for her in the future. So first up, what is AtomDB? Well, it is a project to bring together atomic data and turn it into useful spectroscopic data. That is the sort of overall overarching summary. We take atomic data from a wide range of sources, wavelengths, atomic structure, and so on. We put them into standardized formats, and then we process them to produce either emissivities, which observation codes can use to compare models with spectra, or so that's this sort of section over here with the Sherpa and the Chow and the XSpec. We interact directly with other models. Some of ours, APEC is our main one that we use. We have other models based upon the database that we use. And then there are the sort of access to the database tools themselves. So this is our PyAtom DB and WebGuide interfaces. So if you want to know what a collision strength is between two levels, you can actually go and look up the raw atomic data, this sort of interaction here. Ultimately, our goal is to take atomic data, which sort of for one ion here looks like this, a total mess of cross sections. These are collision strengths actually for one transition, and make you not have to worry about that. We fold it through our plasma code, it produces emissivities. You can then model this is the spectra of two stars, AB Dor and Alpha Centauri, and all you should have to do in your modeling code is press model APEC and fit, and you should get an answer. Obviously, you can do much more than that. The whole database is very powerful. You probably should do more than that, but the idea is that you don't have to know all the atomic data to be able to at least interpret your spectra at the basic level. Okay, so what's new this year? Mostly this year, we haven't focused too heavily on updates to atomic data that underlies the database. There's been a lot of enhancing, or sorry, expanding the database to include new processes, but the existing data that was there before is still there. So if you're looking for a new collision strength or anything, that hasn't happened this year. What we've been doing instead is focusing on accessibility and the software. So the PyAtom DB interface, which is our main way people can interact with the database, has been vastly expanded and rewritten. It now, dare I say it, is almost user-friendly. The charge exchange models have been released. I'll talk about these more. We now have non-Maxwellian electron models as well. We've worked on our XSpec and Sherpa integration for the Python routines, and we've made updates to the website. And there's been upgrades and new work on the uncertainties as well. Okay, charge exchange models, we'll start with those. This is our biggest enhancement to the database. These now include real cross-sections from the University of Georgia's Chronos database. We originally made a charge exchange model about 2014, which was sort of the simplest charge exchange model you could have. So charge exchange is when you have a neutral and an ion coming together, and the neutral transfers its electron into the ion, which is captured into a highly excited state and works its way down to the ground, giving off a distinctive set of photons on its way, because it's captured into a state which is rarely excited by collisional excitation. Previously, we just sort of used empirical formulae for these. Now we have the actual cross-sections, velocity-dependent cross-sections from the Chronos database for the bare, hydrogen-like, and some helium-like ions. And this has been implemented in one of our Python routines, which you can now use in XSpec as a model. And this has been used successfully to model the M51 jet region. You can see here, there are this is where the black hole is, and you can see there's a bright cloud here, and it's the jet interacting with the cold gas, giving distinctive charge exchange lines, which are shown here, and it's the oxygen with the pink lines here. So this is sort of available, you can use it, it works. The other major release is the non-Maxwellian modeling package called Kappa. So this is a for non-Maxwellian electrons could arise when, for example, you have a sudden shock accelerates your electrons. So instead of having a Maxwellian distribution of electron energies, some of those low energy electrons get bumped up to high energy, and you end up having this high energy tail. which is not well represented by any of the Maxwellian models that we have. However, atomic data is by and large, for collisional processes anyway, collected on Maxwellian temperature grids. This is because it's easier. You save a lot of disk space by averaging very detailed cross sections over a Maxwellian. The downside of that is if you want to then model a kappa distribution, you can't, or any other electron energy distribution. So this model was produced based on work by Daniel Savin and Mike Hahn, who produced a sort of sum of Maxwellians approximation. So you add up or subtract Maxwellians to approximate the electron distribution of a kappa model. And we implemented this. Xiaohong Kui did this work in this paper here. And this is now released, and you can see the effects of this. So this graph here is showing the different contributions from different temperatures components to the oxygen-like helium-like triplet. And the red line, which is going off the top of the screen, shows the Maxwellian result for the same plasma. And you can see that not only is the line ratio slightly different, rather than being sort of a 3 to 2.5 ratio, it's more like a 2 to 1, but also the amplitude is significantly smaller. So the Maxwellian plasma has a significantly different signature to the kappa plasma. And anyway, this is now modelable again. You can load this model up in XSpec, and you can play with this now. Okay. Next, Electron-Electron Bremsstrahlung. So this is a model we've had going for a while. It's been essentially electrons, when you get into relativistic speeds, the Bremsstrahlung emission from the electrons is no longer self-absorbed. So at low speeds, electrons have Bremsstrahlung, which is when they interact with each other, change direction, give off photons due to the change of direction. And those are normally just reabsorbed by other electrons. You don't see anything. When you get up to relativistic energies, the energy balance changes and the photons escape, and you can see this emission. As a result, once you get above temperatures of about 10 keV, this becomes quite significant. This hasn't been included in AtomDB in the past because people don't usually look for line spectra of 10 keV plasmas on the grounds that there aren't a whole lot of lines. But it does actually make a difference when you're looking at comparing to other databases. And it does make a difference when you're trying to model objects like some white dwarf shocks, accretion shocks. So as the electrons approach, these models are now available in PyAtom DB again. They will be released in the standard APEC model. We have to sort of talk to the XSpec people, probably Keith, about how exactly to do that so that it's done automatically, but it is a thing that exists. Okay, so now back to PyAtom DB. PyAtom DB is an ongoing project to open source all the atomic codes and models within Atom DB while providing easy access to the underlying data. It's a Python module. It's on GitHub. You can go and get it. You can install it in your Python install however you want. It has documentation. The main virtue of the PyAtom DB process is that previously our project was run by a combination of C code, C++ code, IDL code, Python code, and everything was sort of individually separated, and bits would work here and there. And crucially, when we ran a model to update some of the emissivity files, it would pull from different places depending on what the model was, and there was no real consistency. So the idea of the PyAtom DB project is to standardize everything. You can now, if I'm making a charge exchange model, or I'm making a collisional excitation model or anything else, I can just tell it to use the same atomic data because it's using the same calls, the same routines. It's easily extendable, and it can be used by users to make spectra and by me to make new data files for people to use in analysis tools. It has many modules in it, excuse me, but the three important ones are APEC, which is our plasma code, which has been running since the 2000s. It's the thermal plasma model, reads in the atomic data, makes a collisional radiative matrix, and spits out the emissivities. That now is entirely in Python. You can run it yourself. It's quite slow. It needs some work, but it does work. And it's what's used to make our recent releases of AtomDB. The AtomDB module itself is used for getting atomic data in and out. So if I want to know what a cross section is, or a collision strength, or an A value, or any of that, you can just ask it. This is an advantage because our data is open source. However, it's also a lot of it is stored as formula or fitting formula, which are not always easy to interpret. So if I tell you that the cross section is, it's A plus B minus C, if you don't know what A plus B and C are, it doesn't matter. Whereas this will just say, you can tell me I want to know what this ionization rate is, and it will spit you out the actual number. And then there's spectrum, which is what I think most people would use, which is actually creating spectra from the emissivity files. So that I could talk a lot more about the PyAtom DB stuff, but I figured that that's more open to demonstration. There are documentation on the web. If you have any questions, feel free to ask me. But I am also aware that watching somebody talk about code is not an interesting talk. So, other thing we've updated is our online tools. We've had this web guide for a very long time. You've always been able to go there, ask it what lines appear in this wavelength range, what transitions are here, what is that transition? When you say the transition is 7 to 1, what is it? And it tells you all the electron configurations and the energy level sources and so on and so forth. The new feature we have is replacing an AtomDB app. Many years ago, we made an app for AtomDB, which let you plot spectra and look up the lines in the region and all kinds of things. And it was designed for the iPad 1, I believe, which was a long time ago. But we realized the problem with designing apps, which, while they're really cool and people like them, is that you have to keep updating them, even if you don't change anything, because Apple changes interfaces, rules, hardware. Unless you're a professional programmer, it's a lot of work. And none of us are professional programmers with that much spare time. So we now have made a website which does this for you. So essentially it's the app, but online. You can plot spectrum, you can change response files, change the temperatures, and it will live update the spectrum. You can add velocity broadening or remove it. And you can hover over all of the lines on this graph and it will tell you what the lines are. And if you click on them, it will take you to that previous page, which actually explains what that line is. So, this is magnesium 12, 3 to 1. If you click on that, it will tell you what that means, where the information came from and all that, so on. So this is a new interface, and we're working on improving it to include more different models, because it currently only does our equilibrium model. But any feedback is welcome as to whether this works or not, and whether this is interesting. Okay. Other changes. So this is our standard temperature grid for AtomDB was to store 51 temperatures. So we run the emissivity code 51 times at 51 different temperatures and produce emissivities each of those temperatures. So 51 blocks of data, one for each temperature. And then when codes like XSpec created the APEC model, they would interpolate between these two. So they would say, okay, I have a temperature stored at 1 million degrees and 1.1 million degrees. You've asked for 1.03 million, so I'll interpolate between those two neighbors and get you the spectrum. We've known for a while that this is not perfect because the grid spacing was rather large. It has become more apparent with more people looking at it. The gaps are too large, essentially. There was work done by Francois Mernier and all who sort of pointed this out in detail. So we've now changed this from being a 51 temperature grid to a 201 temperature grid. This takes the worst case error. If you were really unlucky, you could get some abundances would change by about 20%. That was a very much very worst case scenario. Now, from all the tests I've done, the abundances stick within 3 to 5% of what they would be if accurately done.
3 minutes, Adam.
Yep, thank you. So that's now released. There are several updates here. You can do the temperature grid. You can change. There are other suggestions on here that you can implement as you wish. Okay, so now the final thing I want to talk about is uncertainties on atomic data. So this is an ongoing project that we have. This is something that fascinates several of us because atomic data is treated as being 100% accurate in all models. It is not. If you try and fit something in XSpec, it says the atomic data is perfect. So estimating what the atomic data uncertainties are is important, and figuring out what to do with those is also important. However, both of those are beyond the scope of either humans to do right now. So what we're doing is looking at the atomic data that exists and figuring out what uncertainties those have. One calculation of an emissivity will involve millions of numbers, excitation rates, A values, a very complex matrix that you have to solve. But if you simplify it down to ionization and recombination rates, you take out most of the complexity. Ionization and recombination rates for iron, you have 26 ionization rates and 26 recombination rates, not a million numbers. And they'll have a very significant change on your spectrum, because if you change how much iron 15 you have, you change the strength of all the iron 15 lines. So our student Kerry Hure looked at collected all the data from the various public collections released over the last 30 years or so to figure out where the atomic data came from, and crucially what the experimental uncertainties on that data was. She found roughly, and this is a rough approximation, there was a 25% uncertainty on recombination rates and 15% on ionization rates, roughly speaking. So what does that mean? Well, if you look at the ionization recombination rates, here you see the this graph is showing the range on each population. So the sort of canonical result is the solid line, and the shaded area is plus or minus 1 sigma for the ionization and recombination rates, and the effect this has on the ion fraction. And crucially, what I want to point out here is for the ions that you think you know, like helium-like iron, which is the purpley line here on the right, the uncertainty is still about 5%. At best, you know the population to 3 to 5%. For the L-shell ions, the ion population is known no better than 30%, if you believe the experimental uncertainties on the ionization and recombination rates. Those are large numbers. I don't claim that they are. They are the numbers which are correct given the experimental data and published uncertainties. Do we believe we don't know these results to 30%? I don't know. That's a question for the reader and for a lot further discussion. Significantly, if we look at all of the collections over the last 30 years and their results on the ion population of these 3 ions of iron, all the different shapes represent different data collections. And you can see that essentially they all lie within the error bars. Like the result they have on the ion population is mostly within the error bars that you're seeing here of the experimental uncertainty. So we sort of frequently revise these data sets to be in the error bar. Does that mean the error bar is too big? This is again a discussion point that we should have. And how significant is this? Well, this is the just briefly. This is the Hitomi spectrum from Perseus. The black line here shows the same spectrum, but taking away the helium-like iron contribution. So the 4 main lines, you set them to not exist, and you still have 20 to 30% of the flux left in this band, and that's nearly entirely from lithium-like, and some beryllium-like iron. If you don't know how much lithium-like or beryllium-like iron you really have, which is what that previous graph was showing, then this 20 to 30% of the flux could easily become 10% of the flux or 40% of the flux, which will change the results in this region quite significantly. Similarly, the ion population itself is driven in large part by, for some lines, by recombination or ionization. If you look on the bottom pie chart on the right, the yellow, pink, and red sections are ionization and recombination driven. So they're driven by the population of the other ions, not just the helium-like. Okay, I probably am out of time, so I'll just leave you the slide showing our upcoming plans for the rest of the year, and you can ask any questions.
Okay, excellent, Adam. Thanks very much. We have 1 comment and 1 question already. The comment is from Martin Lamming, noting that the electron Bremsstrahlung is 0, not necessarily because of self-absorption, because the wave train from one electron is exactly canceled by the wave train from the other electron in the scattering, and then you get destructive interference, which is equal and opposite. But then Chris Stone has a question regarding the iron L-shell charge state distribution uncertainties. Is the 30% saying that the 25% in each individual rate is uncorrelated, or are they correlated?
So the fact that, yes, so the minimum uncertainty that I've put there, this graph here, where the big red arrow is, that is assuming that everything is uncorrelated. There's no assumption there of correlation, which is probably not true. But when you look at experimental results, they just list an uncertainty of 15%. So I don't know whether that's meant to go up or down. That's that's something we should look into.
Okay. Next question. Are there plans to update the AtomDB to take into account high resolution spectroscopy from upcoming telescopes like PRISM, especially in the calculation of metallicity?
I mean, in general, yes. What specifically about the calculation of metallicity would be, I mean, yes, it's not ongoing project is to keep updating AtomDB for PRISM, yes.
Okay, yeah. And sorry, I should note that question is from Anwesh Mamjuder. And my apologies for mangling names throughout this entire meeting. From Preeti Vishwakarma. Hello, Adam. For which ions is atomic data not available at OpenADAS? And can we calculate it, or can we give some external data file?
OpenADAS?
OpenADAS.
Okay. Good question. We should talk to the OpenADAS people about that. So ADAS is a different project. There are, if you're asking what data do we have that they don't, there is an awful lot of overlap. Mostly it's just different data sets. ADAS is concentrating on the fusion world, so you have a lot of tungsten data, which we don't have a whole lot of interest in the astronomy world. But a lot of it is about building it into sensible formats. So the ADAS data is, we use a lot of the ADAS data. There's a lot of overlap because a collision strength is a collision strength. But as to what they don't have specifically, I'd have to look into it in more detail.